All right, section 3.3, graph sketching, asymptotes. Back in the first two sections of this chapter, 3.1, 3.2, we talked about how the first and second derivative give us information about the shape of a graph, the behavior of a function. The first derivative we could use to determine whether the function is increasing or decreasing, maybe where there were relative maximum or minimum values, right, those turning points on the graph. The second derivative told us about concavity and that shape or that behavior of the graph of the function. Inflection points, right, where you had a change in concavity. But it was more about the shape of the graph itself. This section continues to talk about graphical characteristics or information that I can use to help give me an idea of what the graph of the function looks like, or more importantly, just what the behavior of the function is. And as we keep talking about with this stuff, the math part of it, where we're looking at a graph, yeah, but I can always just graph the function on the calculator, big whoop. But what does that tell me about the behavior of the function when we're talking, say, about application type problems? The function that we're dealing with. What is that function's characteristics? Right? What happens to my function values as we move across the domain of that function? That's the big takeaway from this. That's the useful part of this. So we can use the graph to give us a visual of that, but ultimately it's just all about having that idea of what the behavior of the function is. So we're going to start with vertical asymptotes. Now, a lot of this you may remember from algebra, because we do talk about vertical and horizontal asymptotes in algebra. So some of this should be reviewed, but we're going to get a little more into the specific type of description or definition that we use for calculus as opposed to what we talk about in algebra. And to do that, I'm just going to start first with these two examples, because these would be functions that are familiar to us. We talk about these rational functions, like that first example, f of x equals 1 over x minus 2. The function is undefined, right, where that denominator equals 0. And so what you get on the graph of that function at x equals 2, where that function is undefined, is one of those vertical asymptotes. But, visually, what's the behavior of the graph at a vertical asymptote? Well, the graph gets closer and closer to this line, right, without ever touching that line. We know it can't ever hit that line x equals 2 because the function is undefined there. Right? Now, also keep in mind that when we talk about a vertical asymptote, it is a vertical line. And so when we give the location of, or we identify a vertical asymptote, it should be given in the form of the equation of a vertical line, right, which is x equals whatever that number happens to be. Another type of function that we've talked about were those log functions, and we spent a lot of time talking about the natural log function in particular. So for this example, g of x equals natural log of x plus 2, this function also has a vertical asymptote on its graph. Now this, again, comes from the domain of that function. Remember, the domain of a log function, whether it's natural log or any other log, that argument, x plus 2, has to remain positive. All right, that was by definition the domain of a log function. And solving that inequality, we get x is greater than negative 2, so that tells us that the graph of that function should lie to the right of negative 2. We know the graph can't ever hit or have a point located at negative 2, so we get this same type of behavior that we had with that rational function above. The graph of that function is going to get closer and closer and closer to that vertical line, x equals negative 2, as x gets closer to negative 2. Right? So that's just kind of the visual. That's, how we describe them just in general terms. But we need a little more general definition, because different types of functions, how you identify or where the vertical asymptotes are located, it's done differently, right? Because with the rational function, it's where the denominator is 0. With the log function, it's where the argument is 0, right? It's where we find those vertical asymptotes. So we need a little more general definition as far as what exactly a vertical asymptote is, and we can apply that to any type of function that we're looking at. So this leads us to this more formal, call it the calculus definition of what a vertical asymptote is. We'll say that a vertical asymptote on the graph of a function f of x is a vertical line whose equation is x equals a if either the limit as x approaches a from the left of f of x, or the limit as x approaches a from the right of f of x is either positive or negative infinity. Right, so if you look at the graphs of those two functions, right, as x approaches 2 in the case of our first example f of x, what happens to those function values? Right, the function's either going off to infinity as we approach 2 from the right, or it's approaching going off to negative infinity as we approach 2 from the left. And so go back and remember our limit definitions and talking about left and right hand limits, one-sided limits, as x approaches that number from the left or as x approaches from the right. And in this case, our a value is 2. In that second example, our a value is negative 2, right? That's the behavior that as x approaches negative 2, in this case from the right, the graph of that function is approaching that vertical line x equals negative 2, right? And the behavior of the function is that its function values are approaching negative infinity. So the more formal definition of a vertical asymptote is you're looking at any point on the graph where as your x value gets closer to that point or that value, the function values either shoot off towards infinity or negative infinity. And that's how you identify a vertical asymptote for the graph of any type of function. And this is just, again, as I mentioned, review, recall in terms of domain, and we'll talk about this going forward. The domain of a rational function, right, f of x equals p of x over q of x, we're going to talk about those in quite a bit of detail, is the set of all real numbers, except where that denominator, q in this case, is equal to 0, right? So we say we always set the denominator equal to 0. Any value that makes that happen is not in the domain of our function. And as we just mentioned, the domain of those log functions, log base a of x, or, you know, we focused a lot on the natural log function, log base e. But in either case, the domain would be the values of x, or more generally the argument, right? So it didn't necessarily just x, but whatever that argument happens to be, such that the argument is positive. Right? So that's what we did in our example. We said x plus 2 greater than 0, solved that inequality, and we had the domain of our function. Okay? So as always, different types of functions, how do you determine their domains? It depends on the type of function. Now, be careful with rational functions, okay? There's a little bit extra to this, whether you're talking about domain versus the location of vertical asymptotes. So if we have a function f of x, p of x over q of x, a rational function, f of x has a vertical asymptote whose equation is x equals a, right, that vertical line. If the denominator is 0, here's the extra piece of this, though. Only if that function is in simplest form. And what does that mean? Well, for a rational function, it's a fraction. I want that fraction in simplest form. How do we simplify a fraction? Well, we look for common factors between the numerator and denominator. So for a rational function, we want to factor the numerator and the denominator completely. Look for any common factors that we can divide out. Right? Now, the domain is still based upon the original function before you do any simplification. So anything that makes the denominator 0 will not be in the domain of your function. Then we look to see if the function can be simplified. And anything that remains in the denominator after simplification that would cause that denominator to be 0, that would give you the locations of your vertical asymptotes. Another way to look at this, and this goes back to something we've talked about before when we were evaluating limits especially. We know that there's going to be possibly a vertical asymptote where the denominator equals 0, right, where q of a equals 0. If you look at a value that makes your denominator 0, and it also makes your numerator 0, that is an indication that whatever that factor is in the denominator that causes it to equal 0, I would be able to divide that factor out because there would be a common factor in the numerator that would also make the numerator 0. Right? It's just another way to look at it. I mean, it's in this case, in this idea of if you plug a number into your function and the denominator is 0, we know that number is not in the domain of our function. But there may or may not be a vertical asymptote there depending upon if the function is in simplest form or not. And a way that you can identify that is to plug that number into your numerator as well. And if I get 0 in the numerator also, then that tells me that that number is not the location of a vertical asymptote. It is not in the domain of our function, but there is no vertical asymptote there. So it's just another way to look at it. For our purposes, though, I'm just going to approach it from simply factoring, right, and looking to see if the function is in simplest form. So, for example, f of x equals x minus 2 over x squared plus x minus 6. If we factor that denominator, x minus 2x plus 3, which we need to do anyway, even if we're going to find our domain. Now, again, be careful what it is that you're looking for. If I'm looking for the domain of that function, then I take its denominator, I set it equal to 0, factor each factor equal to 0, solve those equations, and in this case, we get x equals 2, x equals negative 3. Those are the values that are not in the domain of our function. I call them domain restrictions. That's the term I use. So we know that the domain of that function f of x would be all real numbers except for 2 and negative 3. And there's a reminder about interval notation. Right? So our domain would be all real numbers from negative infinity to negative 3. And then we leave negative 3 out and we catch everything between negative 3 and 2. We leave 2 out, and then we catch everything from 2 to infinity. Right, so that's our interval notation, just taking the union of intervals from negative infinity to positive infinity, throwing out any of those domain restrictions. Now again, that's the domain of our function. If we're looking for vertical asymptotes, we also first want to make sure the function is in simplest form. So because this function has a common factor of x minus 2, right, in that numerator and in that denominator, I can divide out x minus 2, and this goes back to what we had mentioned up here, the fact that 2, when I plug it into that function, we know it's already not in the domain. It makes my denominator 0, but it also makes the numerator 0, in this case, if we plug 2 into that function. So I can divide out that common factor of x minus 2, which leaves us with 1 over x plus 3. Then I identify vertical asymptotes from any of the remaining values that make that denominator 0. So in this case, x equals negative 3 would be the location of our vertical asymptote. But it's the only one. Now, 2 is still not in the domain of our function. So if I graph that function, or look at the graph of that function, there is no point on the graph where x equals 2. So there's no vertical asymptote, but what you get on the graph itself is just a hole in the graph. Right? When you graph on the calculator, you always want to be careful about the calculator. As you get into more intricate types of functions and you bring in more of these graphical characteristics, the calculator can only do so much. I mean, it's not always going to give you a perfectly 100% accurate graph, or at least to where you can see everything clearly. The calculator will not graph these little holes in the graph. Right, you graph this function x minus 2 over x squared plus x minus 6, you're going to get exactly the same graph as 1 over x plus 3, right? Because these are equal to each other. They're the same. But the only difference is my function 1 over x plus 3, that's defined when x equals 2. So when you look at the graph of that function, there's no hole in the graph at x equals 2. But there is a hole in the graph for the original function because that one is undefined where x equals 2. But either way, the calculator, if you graph the original function, it does not graph those little holes. Now, if you zoom in really, 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 really close, so if you graph that function and then you zoom in really, really, really close to the point where x equals 2, you're going to see a little tiny gap in the graph. But you have to zoom in really close to see it. So that's how the calculator, I mean, it doesn't graph or plot a point there. You just don't see it when you graph the overall function. Now, for our purposes, again, that's just for reference sake. I mean, we're interested in those vertical asymptotes, right? So, yeah, distinguishing between the domain and location of vertical asymptotes. So that you want to be careful. So if I want the domain, that's done as we always have. Where is the denominator equal to 0? If I want the vertical asymptote, first make sure the function is simplified before you identify the location of the vertical asymptote, right? For rational functions. Horizontal asymptotes, right? Same basic idea as verticals, but obviously with respect to the horizontal instead of the vertical. Now look at the graphs at the bottom. Right, so here's our f of x equals e to the x. Right? We talked a lot about our natural exponential function, and the graph of that function has that basic shape where this piece of the graph, this left side, is getting closer and closer to the x-axis, but it never hits the x-axis. We said, and we've said on many different occasions, that e to the whatever, right, whatever x happens to be, you take e and raise it to a power. Remember, e is a number. It's a positive number, 2.72 approximately, but it's a positive value. And if I take a positive number and raise it to any exponent, you're always going to get a positive number. So when we talked about our exponential functions, base e, or in general for any positive base, which is our basic definition for exponential functions, we know that the graph of those functions will lie above the x-axis. The function value will always be positive. It will never be zero. It will never be negative. And so you get this type of behavior again with respect to the graph approaching, in this case, the x-axis, that horizontal line, as our graph moves to the left, as x approaches negative infinity. And to see it a little clearer, I took e to the x and we did a vertical shift on this. Remember, if I just take the function and subtract the number, then graphically you get that vertical shifting up or down. So in this case, shifting down 2 units. Well, again, there's still going to be a horizontal asymptote because all I'm doing is taking that graph of e to the x and I'm shifting the entire graph down 2 units, including the horizontal asymptote. So y equals negative 2, all right, equation of a horizontal line, y equals, is a horizontal asymptote on the graph of that function, and the graph would approach that line as x approaches negative infinity. Right? So this will give us our kind of our general definition of how we defined, in terms of calculus, a horizontal asymptote on the graph of a function. So our definition above, a horizontal asymptote on the graph of a function f of x, is a horizontal line whose equation is y equals a number, right? Horizontal lines y equals, vertical lines x equals. So let's make sure we're not getting those wires crossed. If either the limit as x approaches infinity of f of x or the limit as x approaches negative infinity of f of x is equal to some number, is equal to b. And in this case, b is 0 in the first example, and b is negative 2 in that second example. Right? In behavior, right? You may remember that again from algebra. We talk about in behavior with like polynomial functions, but it's the description of what the graph is doing as x approaches infinity or negative infinity. Right? As you approach negative infinity, that's what's happening on the left side of your graph. If you approach positive infinity, that's what's happening on the right side of your graph. So it's the in behavior. So that's what horizontal asymptotes actually are. It's a description of the end behavior of the graph of your function, which means, and kind of keep this in mind, I see misinterpretation of this sometimes. That is strictly describing what happens on the far left and far right of your graph. It tells me nothing about what happens in the middle of that graph, right, or the rest of the graph. So a common misconception is, like with vertical asymptotes, we know a graph cannot cross or touch a vertical asymptote because the function is not defined at that value. That's not true for a horizontal asymptote. A graph can cross a horizontal asymptote. It can cross it many times. It just depends on the graph of the function. But what the horizontal asymptote tells you is what happens to the graph on the far left and on the far right, right? As x approaches negative infinity, as x approaches positive infinity. Right? So there's a difference. The only thing that vertical asymptotes and horizontal asymptotes have in common is the name asymptote. Right? What they describe are two completely different concepts. So I don't want any confusion there or any misinterpretation. Right? So vertical asymptotes tell you one thing, horizontal asymptotes tell you something completely different. Now, for rational functions, these can be a little bit trickier. So we said for the exponential function, it's pretty straightforward. Every exponential function has the same basic shape to its graph, so it's easy enough to identify where that horizontal asymptote is. For a rational function, though, it's a little bit more involved. Right? So rational functions, f of x equals p of x over q of x. To determine if there, first of all, is a horizontal asymptote, we compare the degrees of the numerator and the denominator. If the degree of the numerator is less than the degree of the denominator, then the x-axis, whose equation y equals 0, is a horizontal asymptote on the graph of that function. So for example, f of x equals 1 over x minus 2. All right, the numerator is degree 0, the denominator is degree 1. Automatically, I know that the x-axis is the location of our horizontal asymptote. And again, the equation there is y equals 0. We're always giving the horizontal asymptote as the equation of a horizontal line, y equals whatever that number happens to be. Right? Now, we also have a vertical asymptote at x equals 2. Right? I mean, the function is undefined at x equals 2, so there is a vertical asymptote there as well. Second possibility, if the degree of the numerator is equal to the degree of the denominator, then the equation y equals a over b is the equation of your horizontal asymptote, where that a value is the leading coefficient of the numerator and the b value is the leading coefficient of the denominator. So for example, f of x equals 3x minus 1 over 2x plus 2. Since the numerator and denominator both have degree 1, then I look at the leading coefficient of the numerator and denominator. That's your a and b values. So the horizontal asymptote here would have the equation y equals 3 over 2. And I've sketched in a graph of what that function looks like. You also have, again, a vertical asymptote where the denominator, 2x plus 2, would equal 0. And if you solve that for x, that would give you x equals negative 1 as the equation of your vertical asymptote. Right? So obviously, when we're dealing with rational functions, you're going to be interested in identifying both the vertical and horizontal asymptotes. Right? So be careful in, again, how you do that, right? How do I determine vertical asymptotes? How do I determine horizontal asymptotes for those rational functions? Third possibility. If the degree of the numerator is equal to the degree of the denominator plus 1, then there is no horizontal asymptote. Or in other words, if the numerator has a degree that is 1 greater than that of the denominator, there is no horizontal asymptote. But the function, the graph, will have what is called an oblique asymptote. It's a slanted asymptote. Right? For example, f of x equals x squared over x minus 1. Right? The degree of the numerator is 2, the degree of the denominator is 1. So there is no horizontal asymptote, but there is this slanted asymptote, and that's what the graph of that function would look like. Now, we're not going to do a lot with these oblique asymptotes. We can at least recognize that there is one there in these cases. Right? We're going to be mainly interested in the verticals and the horizontals, but be aware that there are other types of asymptotes. And this slanted asymptote, that's the terminology that's used in this textbook. We also call those oblique asymptotes. That's a little fancier term for these slanted asymptotes. There is a fourth possibility. If the degree of the numerator is more than one degree greater than that of the denominator, right? So if the degree of the numerator is greater than that of the denominator by more than 1, then the function has no horizontal or slanted asymptote, right? So yeah, there is just a characteristic of that type of function. So for rational functions, a little bit more involved, and so but it's all about the degrees of the functions. And that's really all I'm going to ask you about for those types of functions. Right? Identify the vertical asymptote, identify the horizontal asymptote, maybe match a graph, which again, that's just graphing on the calculator, but again, be careful in terms of what we said about domain versus vertical asymptotes for those rational functions. And then we'll finish up as always with an application. And so this is one that plays a little bit with the existence of a vertical asymptote in particular. Here I've got a fertilizer plant that spilled some chemicals into a nearby lake. Kind of like when they had the train derailment in Eunice and polluted the lake outside of town there, and they just finally got that cleaned up. It was determined that the cost in dollars of removing P% of the pollutants from the lake is given by that function C of P equals 40,000 over 100 minus P. So we've got our function C, which is the cost of removing the pollutants, where P, the input, is the percent of the pollutants that is removed from the lake. So question part A is just a straight evaluation, right? Find C of 0, C of 50, C of 90. So that's just plugging values into the original function. And as I keep telling you, just be careful when you're working with these different functions, especially when you bring in derivatives and that, or second derivatives now also, right? Be careful as far as which function you're actually plugging the numbers into, right? So C of 0, C of 50, C of 90, plug each of those in, like at $400, $800, $4,000. And again, remember that's our cost, right? For removing 0%, technically it's going to cost $400 to remove nothing according to this model. 50% and 90%. Okay. What's the domain of that function? All right, since P represents the percent of pollutants being removed. Now, we haven't, I guess, talked a lot about or made a big issue out of this. You know, we talk about domains of functions. You have domain issues based upon the makeup of the function. You know, like this, in this case, it's a rational function, so I know it's undefined. When P in this case would equal 100, because that would make my denominator 0. And so technically you could say the domain of that function then would be all real numbers except 100. But you also have to consider the context of an application, right? So if I was just looking at that function C of P and said, what's the domain? No, the domain is a set of all real numbers except 100, because that's where the function is undefined. But then when we put this in the context of an application, we have to then take into account what the variable represents, right? So there's more meaning here. So since P is the percent of the pollutants that can be removed, realistically, how much can you remove, right? You can remove none of it, or you can remove all of it, right? Or anything in between. So in the context of what that variable represents, the domain of that function could only be from 0 to 100, right? I can only remove from 0% to 100% of the pollutants. Now in this case, I can't include 100 because of the fraction, the function itself, which is undefined, where P equals 100. So the domain of our function would be 0 to 100, right? Putting the limitations based upon the variable, but then we also have to exclude 100 because of the fraction. And so not only do you have issues with the function itself and the way that it's the makeup of the function, but you also have to take into account the context of the application. And so there may be some implied restrictions or limitations on your variable, depending upon what that variable represents. We haven't really dealt with that a whole lot, but you know, you do have to keep that into consideration. I mean, for the most part, our variables are positive numbers in the applications that we're working with, but here's a case where I do actually have to put limitations because of what that variable represents. Here I'm looking at the graph of the function C of P, and I've done two graphs here. I want to start with the one on the right first, because you know, and now the x-axis, that's our p-axis, the percent of the pollutants that can be removed. So we said that could be anything from 0 to 100. We know the function is undefined at 100, so I went ahead and put in a vertical asymptote, and then I plotted the points that we found back in part A. Right, where C of 0 equals 400, C of 50 is 800, C of 90 was 4,000. And so then I graphed the Y scale. I went ahead and pulled it up to 10,000 just to get a decent view. But notice what's happening to the values of that function. And this fits two formats. It fits what we've seen on the graph of rational functions. It also kind of resembles an exponential function, right? I mean, our exponential function base E, or those exponential functions we looked at, that's really the basic shape of what an exponential function looks like. All right, even though this is a rational function. But notice what happens as we move along the x-axis, as we increase the value of x, the value of the function is increasing, but it's also increasing more rapidly. If you want to bring your derivatives into this, the fact that it's an increasing function means our first derivative would be positive, right? The fact that it's increasing more rapidly, right? The rate of change of the rate of change is increasing. That's our second derivative. It would also be positive, or you could look at the shape of the graph. That's a graph that would be concave up, right? If we follow the shape of the graph, our fingers would bend upwards. That's a concave up graph. So that tells us our second derivative would be positive. And so there you can kind of tie that back into what we talked about in those first couple of sections. Then I also included this graph on the left. Right, so if we zoom out further from our graph, right, we've got that same behavior, but notice I just changed the y-axis in this case. I brought it up to 40,000. You put whatever you want there. But the basic shape of the graph is the same. Right? The observation I want to make here is that, look, as x approaches 100, or as p approaches 100, that graph is still going to have the same behavior, that in that the function values are going to approach infinity. The graph is going to get closer and closer and closer to that line, y equals 100, x equals 100, vertical asymptote, but it'll never touch it, it'll never hit it. So the graph is going to have to continue with the same behavior on the left that we see on the right. Okay? So that kind of leads me into the last question, part D. Can they afford to remove all of the pollution from the lake? And my answer there should be no. Why? Because remember, the function that we're graphing, c, is the cost of removing the pollutants. Well, as we would get closer and closer to 100% of the pollutions being removed, what's happening to our cost? Our cost is going off to infinity. All right? So according to this model, they would never be able to remove 100% of the pollutants because the cost is getting exponentially large. There's a good term, especially when you look at the news today and they talk about all the stuff with the virus that's going on. Exponential growth. When you hear, we talked about exponential growth models before. That's what you mean. That's what you're looking at in terms of what's happening to the function values, right? So they're getting larger, but they're getting larger faster and faster. And in this case, the cost is approaching infinity. So theoretically, there's infinite cost here. You would never be able to remove 100% of the pollutants. All right, that's section 3.3. See you in section 3.4.